Hello, in example 1 here, we're going to find the area between two curves on the interval from x equals 0 to x equals 2. Our two curves are f of x equals e to the x plus 5 and g of x equals 3. So the first thing we need to do is determine which function is the upper function and which one is the lower function. In other words, which one is greater and which one is smaller. So if you were to draw a graph of this, let's turn off the shading for a moment. You can see here that in red, f of x is equal to the e to the x plus 5 function. That's this function here that's in red. It's an exponential function. Let's turn on projector mode so it's a little easier to see. And then g of x equals 3 is the lower function. And we're going to be finding the area between x equals 0 and x equals 2. So this button here will turn on this shading. Now notice that these two functions do not intersect on this region, and that is okay. In a previous video, we said we may need the intersection points to find the limits of integration, but they're not 100% necessary here. So as you can see here, we can actually see that there is an area between x equals 0 and x equals 2 that lies between those two graphs, which is here shaded in purple. So that's the area that we are after. And it is important, though, to know that f is above g on that interval. So the integral we're going to be finding is going to be the integral of f minus the integral of g, which is just the constant function g of x equals 3. So let's go back here, and now we can actually identify what the upper function is. It is the f of x function, e to the x plus 5, which is over here in red. And the lower function, of course, is the constant function g of x equals 3, which is this blue line. So the integral that we're going to compute is going to basically look like the integral of the upper function minus the integral of the lower function. So we're taking e to the x plus 5 is the upper function minus the lower function, which is the constant function 3, dx. And again, dx is required. It's this entire expression here that we are taking the integral of. You can see here, plus 5 minus 3 can be simplified a little bit so that we can integrate that a little bit more easily. So when we do that, we see that this 5 and this negative 3 add to a positive 2. So this is the integral that we're taking, e to the x plus 2. So we need to find the antiderivative of this expression, the opposite of the derivative. In a previous section, we saw that the antiderivative for e to the x is itself. And again, recall the way we check that is if this is the antiderivative down here, we can take the derivative of it, and we need to get back this function, which we do, because the derivative of e to the x is e to the x. For 2, the antiderivative would use basically a special case of the power rule. And so the antiderivative of 2 is 2x. Again, we can check that. If this is the antiderivative, then when we do take the derivative of 2x, we better get back what we started with in the original integral. And we do. The derivative of 2x is equal to 2. So in parentheses, this is the antiderivative, and we are going to evaluate that from 0 to 2 because those are the limits of integration. And recall the fundamental theorem of calculus told us to do this, we're going to subtract the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. So when I do that and plug 2 into the antiderivative first, I get e squared plus 4. Then I'm going to take away what I get when I put the value of 0 into the antiderivative. And so e to the 0 is 1. 1 plus 2 times 0 is 1 plus 0. So I'm going to take away, I'm going to subtract just 1. E to the 0 is 1. So this is the same thing as e squared plus 3. And on my calculator, this gives me about 10.389. And so this represents the area, the shaded area between the red curve and the flat blue curve. And again, if I go back to Desmos, you can see here I've actually computed that. The integral from 0 to do of f of x minus g of x dx is 10.389. And so that's the answer we got back over here.